Hello, everyone. Hello. So today we're talking about an exciting topic, the delta function. We're going to do a delta function. I don't think we'll do Fourier transforms today. We will do that next week. And then you have two more webinars on thermodynamics. And we will have a guest speaker, Toby Petrican. So he's going to talk about the thermodynamics. So let's start. So first, let's talk about an integral which you are familiar with. It's the integral of e to the power minus x squared dx. And the interesting thing about this integral is that because the fact that it doesn't exist. Okay, so the indefinite integral of this function is undefined. Defined. However, if you take the same thing and say, I don't know, minus 10 to 10, intuitively, you might understand that, well, it has to equal to something. Why do I say so? Oh, because if you draw the graph, y equals e to the power minus x squared. It's a normal distribution curve, right? They might not have told you the formula for the normal distribution curve, but here it is. Um, so because we can clearly see that this is a graph. This is a very reasonable graph. It looks very smooth, and it is a smooth graph. And it's y is equal to e to the power minus x squared. It definitely has a finite area. Therefore, when I write this down, it can definitely be calculated. Something finite. And if you put it in your calculator, it will give you a result. A minus 10 to 10 e to the power minus x squared. My calculator is thinking. It's not the fastest calculator in the world. Still thinking. Okay, I'll leave it. Oh, okay, here it is. You can't see, but it gives me a video. Ah, here it is. As you can see, clearly there is something there. 1.7, and that would make perfect sense. Like the area is 1.77, right? So the calculator gives you 1.77. So it's approximately 1.77. Well, why does it happen? Why can the calculator do that and you can't? Can anyone guess or explain why the calculator can do that and you can't? No, I mean you can. It's just What other ways of finding the area under a curve did they teach you at school? Yeah, exactly, Alexander. It does it numerically, of course. What other methods do you know of finding the integral? If you can't integrate, what do you do? You've been taught one of the methods in school. Trapezium rule, yeah, of course. You can use the trapezium rule here with just so the calculator doesn't use the trapezium rule. It uses some more complicated rules. I don't know exactly which one, but there are various rules allowing you to find the area under a curve. But even if you use the trapezium rule with, I don't know, 1,000 strips, you will get the same answer. It will be very, very close to that. So calculator does it numerically. That's why it's able to do that. Even though there's no this function does not have a primitive function, and you can't integrate it. You can't integrate it, but the integral is finite. Well, you know the exact value of the integral. You can find the exact value. And more to that, if you take the same integral but from minus infinity to plus infinity, e minus x squared dx, it's going to be equal to square root of 2 pi. By the way, square root of 2 pi, it should be close to 1.77. 2 pi. Okay, well, not that close, but it's approximately 2.51. Interesting. What if we do 100? I'm doing the same integral, but from minus 100 to 100. Let's see if the calculator can do that. We'll leave it working it out. Okay, so that's an interesting function. You meet it in very many scenarios. For example, the distribution of air molecules moving through the air, the differentiation of speeds, the distribution of well, normal distribution. Well, everywhere where you have normal distribution, you have this graph. This integral over here, it actually does exist. So even though it is technically more complicated than the other one, you can integrate this one quite easily. And what you do is you substitute, you make a substitution, u is equal to minus x squared. So we differentiate that. We get minus 2x. Therefore, you can write this as x multiplied by e to the power u multiplied by du over minus 2x. X cancels, and you're left with minus 1/2 e to the power u, which is minus 1/2 e to the power minus x squared plus c. So interestingly, this has an integral, has an indefinite integral. If you draw the graph, what do you see? It's a very similar curve, just looks like this. Now, looking at this graph, by just looking at the graph, can you tell me the integral from minus infinity to infinity? the integral of this function from minus infinity to infinity by just looking at the graph. Yes, very good. It is 0. You don't need any extra knowledge. Does everyone understand why it is 0? Does anyone not understand why it is 0? Come on, don't be shy. I'm happy to. It's not a. It won't take me only a minute to explain. Okay, this I haven't got a response from everyone, so it's negative here and it's positive here, and you can see that this area has to be is equal to this area, and because this is negative and this is positive, total area is 0. Okay. Oh, so why is it equal? Well, because e to the power minus x squared is an e to the power minus x squared is an even function. And x is an odd function. Is there anyone here who does not know what is an even and an odd function? I'm happy to explain. And if you multiply an even function by an odd function, odd times even makes an odd function. So you can figure out a general rule is that the integral of an odd function is 0. Although technically, yeah. You might be right. Sorry, I might have messed up. Uh, Gaussian. Yes, of course it's square root pi. Oh yes, I got the answer, which is 1.77. So it is. I was wondering where I went wrong. Square root of pi, which is approximately 1.77. 1.77. Square root of pi is 1.7725, etc. Okay, thank you. Okay, so you have an even and an odd function. And everyone knows even and odd functions. Good. Well, I think I've actually solved problem 3 for you. This is from the assignment, problem 3. You can already solve problem A. In problem B, you just need to do integration by parts. Okay. I'm gonna go do a shorter session today, by the way. We'll probably finish. We'll probably finish before 7. Okay. Now the delta function is pretty much the Gaussian except we have it's the Gaussian, except we have like this. It's a modified Gaussian. So this is the standard Gaussian, and if we write down y equals 1 over b multiplied by square root pi, multiplied by e to the power minus x squared over b squared, and add a slider for b. So this is for b equals 1. This is very similar to the standard deviation. And if you change b, now got this one, zero to 10, 0 to 3, with a step of 0.01. Okay, so if b increases, it becomes wider and wider and wider. And if you go like this, it becomes taller, taller, and taller. The interesting thing is that independent of b, if you take the integral of this function, it's going to be equal to 1. Okay? It's the integral, which would be the integral of normal distribution. You've met this. The integral under the under the normal curve is always 1, right? Because that's the normal distribution. And if you change b, the parameter, this is what you can see how it changes. It becomes narrower and taller, narrower and taller. So the delta function is the extreme case. Delta function is the extreme case as b tends to 0. Therefore, delta function is defined as the integral from minus infinity. No, sorry. What am I saying? Delta function is the Gaussian function. Y e minus x squared over b squared. Yeah, okay, so if you take this function and you take the limit of this function as b tends to 0, and that's what we call the Gaussian function. So the delta function. So basically what it is, the delta function is 0 everywhere, but infinitely large at point 0. The delta function. This is x. This is 0. And this is delta x. Okay, does that make sense? Any questions so far? And the surprising fact about the delta function is that you can take the integral, even though the function is nothing everywhere and except in zero where it's infinitely large, the integral from the delta function dx is 1. Because the integral of any Gaussian is 1. Well, sorry, of a very, uh, oh, the integral of the normal distribution is 1. So, yeah. And you can explore this a little bit. So, for example, if you have a constant, so let's say a is a constant, then the integral of a multiplied by delta x dx is a. Because you can take a out of the integral, very simple, and then it becomes like this. Okay. Now, if you can shift the delta function, shifting the delta function. So, for example, if you have x, the function, if you were to sketch some function. So let's this is y, this is x. X, y. This is delta x. If you were to draw delta x minus 3, it would be a shift to the right. So you can shift it as any normal function. So 1, 2, 3. So 3, 0. And this is delta x minus 3. What do you think the graph of delta x multiplied by delta x minus 3 would be? What do you think that would be? Or for that matter, what would the integral be of delta x times delta x minus 3? So this is delta x. This is the graph. The integral of delta x is integral of delta x from minus infinity to plus infinity is 1, of course. The integral of minus infinity to plus infinity from delta x minus 3 dx is also 1. Yeah, because shifting it doesn't change the shape. The integral is still 1. Have I lost anyone, or is it too simple, or is it? Can somebody tell me what is delta x times delta x minus 3? What's the integral of that going to be? What do you think? Still 1. Well, the delta function is 0 everywhere except when it isn't. So if you multiply them, it's going to be 0 multiplied by a finite, well, by finite, by something finite. So it's going to be 0. It's actually quite simple. This is going to be 0. Because it's still, the other function is still 0 when the other one isn't. So if you take the integral, So it's going to be 0 times the value of that integral, 0 times 1, which is 0. And if you do plus, if you do the addition of the two, then it's going to be 2. The integral of delta x plus delta x minus 3 dx, that's going to be 2. Does that make sense? Because you have the integral of that. And also that follows from the fact that the integral is linear. So you can have the integral of delta plus the integral of delta minus of x minus 3 is 1 plus 1. Okay. Now, if you were having, let's say, a function, if you were having a function, so let's say function, this is f of x, and x, and you have delta x, which is this one, delta x. What would the integral of minus infinity to plus infinity of delta x multiplied by f of x be? What would that be? It's in the assignment, but it's a good question, Andre. What I was thinking when I was writing it down. I don't have an immediate answer for you right now. You have the zero function. I think if you because the delta function is defined as the limit of the Gaussian function, which depends on b, as b tends to infinity. So delta x. So delta x times delta x minus 3 would be the limit of the Gaussian function, b tends to infinity, of x times the Gaussian function of x minus 3. And from that perspective, because because you're talking about a zero, because this is going to be 0, multiplied by something non-zero. So at any point, you have 0 times, well, times that fi finite. We are looking for the total area of 0 at any point. At any point, it's going to be 0. At any point, the function is going to be 0. Therefore, it's the limit is going to be 0. Does that make sense? Okay. I mean, here I am cheating a little bit here, but you can okay, I would probably use this. This is delta x times like this. If you use this, then you're safe. Because this is exactly 0. And this is not something finite, but not 0. And if you take b, for whichever b you take, the answer is going to be 0. Okay. So hope that makes sense. If you make a sequence of these as b tends to, sorry, not infinity, of course, but 0. B tends to 0, tends to 0. Okay. Okay. So what would I get if I multiply the delta function by just a regular function? What would I get? It would be 0 everywhere except at 0. Yes. And at 0, it will take the value f of 0 because you're multiplying delta x multiplying by f of x, which makes it f of 0. So the answer is f of 0. Yeah, f of 0 is this value, is the y-intercept. So if you multiply the delta function by f of x, you just get f of 0. If you get minus infinity to plus infinity of delta x minus 3 f of x dx, you're going to get f of 3. Well done, of course. And so let's test it. Let's test your understanding. Infinity plus infinity. Delta x minus 7 multiplied by x squared minus 4x plus 3 dx. What's that going to be? $24. Yes, well done, Edith. 24. Okay. Does anyone not understand why it is 24? Does everyone understand that it is 24? Okay. And Paula, you've been quiet. Sorry to. Okay. Maybe you just joined because there were fewer people. Now there's more. Okay, that's fine. So you understand that, and that's it's a powerful thing in maths. You need to think of the delta function as not a function in the traditional way. It's more like a distribution. And indeed, if you think about a point mass, for example, a point mass. So use of delta in physics. So for example, a point mass at x equals 4, right? So you have x, and this is the density. Well, this is the density distribution. This is the density distribution. Like if you have I don't know if you have something that is not a point mass. So for example, if you have a rod, yes, if you have a uniform rod like this, so you would have 0, 0, 0, then up like this. Okay. But if you have a point mass at a point x equals 4, it would be the density is going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and suddenly up, and then so the density could be written as 4, oh sorry, is the mass multiplied by delta of x minus 4. So this is a very useful way of dealing with point objects in physics. So you can think of the delta function as just a tool. It's just a very useful tool. It has 0 spatial dimensions. And yeah, of course you can for a small mass you can just use the Gaussian. But yeah, just a useful tool mathematically. Okay, so well we have already shown that the integral of delta x is 1, and we've actually shown this as well. We've solved these. We've solved this already. Okay. Problem 5. Heaviside step function, theta x. So the step function, and it looks like this. It's 0, 0, 0, and then suddenly becomes 1. It's y, is x. Right, so 1. So if it's 0, 0, 0, and then bam, becomes 1. Now if you look at this section, at the gradient at this section, like you could draw a sequence of lines. I won't be doing the whole problem, which is I'm just showing you some hints of how to think about it. Okay, so you could think of it going like this, and then steeper, and then steeper, and steeper. So the gradient is 0, if x is not equal to 0, and the gradient is infinite if x is 0. What function do we know that has the same properties? Well, I mean, we've only been studying one function today, but it is the delta function. So you can see the gradient is 0, 0, 0, and then suddenly the gradient becomes infinitely large, and then again, gradient is 0. So the gradient of the Heaviside function is a delta function. Or in other words, the derivative of the Heaviside function is the delta function. That's it. Quite straightforward, quite an interesting view. Interpret this. I've basically done this section. Interpret this result graphically, but you can solve it, yeah, mathematically. Okay. The last thing I want to talk about today is beats. Beats and sine waves. Beats and sine waves. And sine waves. To do this, I will ask my friend Desmos to help. So we don't need this, don't need this, don't need this. So I'm going to draw. I'm just going to remind you of superposition of waves. Okay, so let's say we have two waves, y equals sine x and y equals, well, 2 plus sine x. Are just two identical waves. If you add them together, y equals, I'm just shifting them vertically. If you add them together, you get, I wonder if I can do this. y1, y2, y2, y equals y1 plus y2. Ooh, beautiful. Lovely. I really like that. So I take a sine graph and okay. Now I take another graph. Y3 is equal to sine x minus pi. And now, and minus 2, like this. Just shifting it down. So if I add y1 and y3, y equals y1 plus y3, you can see that they cancel each other out. Why? Well, very simple, because they are in antiphase. Okay, so these two graphs, peak of one wave meets the trough of the other, and the trough of the first one meets the peak, and together they produce a non-wave. This is superposition, right? Even more precisely, this is interference. This is interference of waves. Okay, is that clear? Do you remember this? I know it's from year 12, but you should remember this. Interference of waves. Now, what if the waves have different frequency? Not just different, but very slightly different frequency. I will demonstrate. So let's call it y4 equals sine 3x and y5 is sine 3.1x. So slightly different frequencies. And you can see that the two waves are almost identical at the beginning, but as time goes on, they go in antiphase. So here you can see they're perfectly in antiphase, and as time goes on, they come back to phase. Okay, this is a tad too long, so I'm gonna make have a more significant change, and you can see that they just do it quicker. Phase, antiphase, phase, antiphase, phase. What do you think if I add them together? What do you think the graph would look like? Can somebody predict the shape of the graph if I add them together? Can you specify what will get bigger and smaller? Yes, the amplitude. Yes, so if I remove these, you will see something like that. The amplitude gets bigger, smaller, bigger, smaller, bigger, smaller. And this is what we call beats. Right? So at the beat, the music beat is actually that. Okay, this is a beat. And you can change the the beats, but if you change beats depends on the frequency difference. So the frequency of the beat is the difference between the frequency. If I do 3.4, 3.3, 3.2, 3.1, you can see 3.2, 3.3, 3.4. I'm just going to increase the amplitude. So let's make it 3 and make it 3 here. Just more pronounced. Let's make it be 5. 5. And let's make it 3. Let's make it 30. And make it this 31. 30.5. Ah, this is beautiful. So the tunes, tunes, tunes. And very easy to demonstrate. If you take a phone, and obviously on your phone you have a signal generator. So sound generator. I'm going to play a note. I'm going to play the A note. Can you hear the note? Or is I think my sound system is blocking. Let's see if I can. Can you hear the note now? It's quiet. Okay. Um,
How about now?
okay. What if I change the frequency? How about now? Eh, okay. Uh, what I'll do is I'll see if I can generate a sound using the loudspeaker frequency. Frequency sound generator. Airline tone. Okay. Okay. What I'm going to do is I'm going to take a video. Hopefully my phone will allow me to do that. And then so right now I have two signals playing at the same time. So they're both 440 hertz. So play and play another one. And now what I'm going to do is going to change this to 141. Hear it now. Ah, what am I doing? Sorry, I'm being daft. Okay. That's very silly of me. I'm gonna stop sharing and I'm gonna share my screen again. Except this time I'm going to use this video, share sound. Sorry, computers. Computer says no. Okay, do you see the screen? Okay. Now I have 440 hertz and 440 hertz, two sounds. So I'm going to play them. Can you hear now? Okay. This is the note A. If you like music, you would recognize the note. And I play the second one. You can see it went really quiet. Why? Because I didn't start them at the same time, so they're in antiphase. So I'm going to play again. Now it's gotten louder. Okay, so I've matched the frequency, because when I didn't start them at the same time, that's why they were in antiphase to begin with. But now I'm going to change that to 441 hertz. I'm going to stop that. So, okay, 440 hertz, stop. 441 hertz, stop. But now if I play them together, that's what we call beats. Can you hear them? Okay. So this is the graph this is the like a siren. Yes, this is what you're hearing. Okay, so 440, 441, but together they sound like this. And if you change the frequency, you can increase the frequency. So the frequency of the beat is the difference in the frequencies. Or you can do, if you do 3. That's quite cool. All right, so that's what I wanted to show you about the beats. And now there are more interesting ways of adding sound waves, even more interesting than beats. So I'm gonna open another one. So let's say we have y equals y1 equals sine x, y2 equals 1/3 sine 3x, y3 equals 1/5 sine 5x, and y4 equals 1/7 sine 7x. Okay, so well, you can predict the shape. I mean, you should know very well by now how they look like. So I'm just gonna draw a graph. Y equals y1. So a sine graph, a beautiful sine graph. No surprises there. Now I'm gonna add y2. And you can see it's still a periodic function, but it's different. It's different. And plus y3. Ooh, interesting. and plus y4. So this is sine x plus 1/3 sine 3x plus 1/5 sine 5x. You will, if you carry this on, plus 1/9 sine 9x and plus 1/11 sine 11x. You get something closer and closer to, well, what you're going to get is a function like this. If you keep doing that forever, you will get a function like this. I'm not 100% sure that the amplitude of this function is going to be 1, but it's going to be a square wave. And basically, that is how you can approximate a constant. So a constant line, so for example, a constant line can be approximated by this Fourier series. This is called a Fourier series. So quite fascinating. And basically, any function can be represented as a Fourier series. So basically, any function can be represented as a sum of sines and cosines, and it's an infinite series of sines and cosines. Okay, I did a silly thing here. Of course, it's not going to be. It's going to be like this. Okay. All right. So I will stop here. I will talk about the Fourier transformation next week. The week after, we're going to talk about thermodynamics with Toby. And the week after, again, even though you would have already submitted the work, there would be another webinar on the 22nd, the last webinar. And this would also be done by Toby. This will be on thermodynamics as well, just to cover up, to go through. All right, then, yes, if you add it become enough, that becomes a square. I will see you next week, everyone. Enjoy.